Welcome to Data Structures. In this set of notes, we're going to talk about three related questions. The first one being, why are we using Java in this course? The second one being, why do we study data structures? And the last one being, why do we spend so much time learning about algorithms? So for many of you, Java is going to be a completely new programming language. You may have come from, say, Python or C++ or some other language that you've used in the past. And because of that, part of this course is going to involve learning the new syntax that you see in Java. But I want to emphasize something right away. This course is not just about Java. Java is really just the vehicle that we're using to learn about these data structures and algorithms. The important ideas that we're going to learn will transfer to almost any programming languages or any programming language that you're ever going to use. So throughout the semester, you're going to see things like lists and queues and stacks, trees, hash tables, sorting algorithms, searching algorithms. All of these ideas exist far beyond just Java. The notes that you're looking at are based on the recommended textbook for this course. Over the years, as you can see, they've been updated quite a number of times, both by instructors and by teaching assistants, including some accessibility updates that were made recently, and also revisions that were made based on some student feedback. So these notes have evolved quite a bit over time. So let's start with that first question. Why are we learning Java? So why Java? One of the biggest reasons we learn Java is because it's important to know more than one programming language. If you only know a single language, then every problem starts to look like something that should be solved with that one language. But once you've learned multiple languages, you start recognizing that different languages are designed for different purposes. Some tools are simply better suited for certain tasks. So for example, Python is great if you're writing these very short, really quick scripts. Let's say you're automating tasks or you're just analyzing some data. Whereas Java is commonly used for larger software systems where maintainability and reliability sort of become important. So neither language is universally better than the other. It's not as if Java is better than Python because you learned Python in CS1 and now you're learning Java in CS2, so therefore Java must be better. They're just different. Okay? They are different tools that are used at different times depending on which one you need. And that's something that you'll discover throughout your career. I mean, experienced programmers, they rarely ask, what's the best programming language? Instead, the question that they're thinking about is, what's the best programming language for this particular problem? So people might debate, I love language A versus language B, but it really comes down to which language is best for the problem that you have at hand. Another reason that we learn Java in this course is that learning an additional language will get easier every single time you do it. So the first language that you use is generally the hardest one that you'll have to pick up. That's because you're learning, both the programming concepts and the syntax at the same time. But once you've already learned, programming, how to program, like if statements, for loops, variables, most new languages are just different ways of expressing ideas that you already understand. An if statement is still an if statement. A loop is still a loop. Variables store information. Functions perform work. The concepts are going to remain familiar. The syntax is going to change, but the concepts are the same. So after you've learned a second language, picking up a third language, or a fourth language, or a fifth language, these things become much less intimidating. And that's one of the major goals in this course. So we're not just teaching Java, but we're hopefully helping you become more comfortable to, adapting to new technologies. Some more information about why Java. Another reason that we use Java is to encourage writing robust software. And what I mean by robust is this. I mean software that's easier to maintain, easier to extend, and kind of harder to accidentally break. So Java includes a number of features that will help with this last goal in particular, where it's harder to break and then easier to extend. So for example, Java supports what we call an immutable value. So an immutable value is this. Once a value has been assigned, we can prevent it from being modified later. And this can eliminate entire categories of bugs that can pop up. So once a variable has a value, you can't change it. And that's an immutable type. Java also uses something called static typing. So static typing is this. When you declare something to be an integer, Java expects it to remain an integer. And the compiler can catch many different mistakes before the program even runs. So if you try and store a string into an integer, Java's not going to let you do it. Another major feature of Java here is what we call visibility and access control or protection. So classes can decide which pieces of information should be exposed and which pieces of information should remain hidden. So we're going to spend a lot of time discussing these concepts like encapsulation, interfaces, public methods, private methods, protected data. We're going to spend a lot of time on those ideas in future videos. So these ideas are going to be extremely important as your software projects get larger and larger. And finally, there's simply just a practical reason. Knowing multiple programming languages makes you more flexible. So when you're looking for internships and jobs, if you know many more languages, you're going to be more hireable, because different companies are going to use different technologies. And the more tools that you're comfortable with, the more opportunities that are going to be available to you. So now that we've talked a little bit about Java, let's sort of move on to the main topic of this course. And it's really, why are we learning data structures? So at first glance, it might seem like we could just store everything in a list or an array. And honestly, sometimes, that's exactly what we should be doing. But not every problem looks the same. Different kinds of data often require different ways of organizing information. So take the image on the left here. Suppose that you have this astronomy image, that's coming from some telescope. How do we store that information in our program? Do we store, every pixel of this picture in a giant list? Do we store it in like a two-dimensional thing where we have rows and columns? Do we break the image up into regions? There are a lot of choices here, and those choices are going to affect how efficiently, we can process that image later on. So now let's take a look at the image on the right. With the image on the right, we have these points that are distributed, throughout this three-dimensional space. Again, we could just throw all these points into some huge, giant list. But then if somebody asks, find all of the points that are near, this particular location, this X, Y, Z location, a simple list might not be the best choice. So this is one of the central ideas of data structures. The way that we organize data is going to affect how efficiently we can use that data. So throughout this course, we're going to be repeatedly asking questions like this. How do we store data? How should that data be organized? What operations need to be performed efficiently? And what trade-offs are we willing to make? Because it's rare for us to find a data structure that does everything exactly like we want it. There are going to be trade-offs. Sometimes we have data that's sorted. Sometimes we have data that we can access data very quickly. So it really depends on what our application is. And that's one of the reasons we learn about this, because we want to know what is the correct data structure for the problem that we're working on. Because there's rarely going to be a single perfect solution for every problem that we're doing. The reason that we study data structures and algorithms together is that they are very, very tightly connected. A data structure is going to determine how information is stored, whereas an algorithm is going to determine how you process that information. Very often, the choice of the data structure completely changes the performance of an algorithm. So consider sorting. There are many different types of sorting algorithms, and you've probably seen some of them in your CS1 class. So for instance, you may have seen bubble sort or insertion sort. You may or may not have seen merge sort or quick sort or heap sort. There are many different ways of sorting data. So the question that you might be thinking then is, well, which one is best? Well, the answer depends on what we mean by best. Do we care about execution time? Do we care about how much memory we're using? Do we care about how complex the implementation is? Do we care about how easy it is to debug? So different situations are going to lead to different answers to that question of which one is best. The same thing is going to happen with our data structures. Maybe one structure makes searching extremely fast. Maybe another data structure makes insertions very, very fast. Maybe another one keeps everything sorted automatically. So every design decision is going to involve some trade-off. And understanding these trade-offs is one of the goals of this course. So we're going to be spending a lot of time, looking inside of that black box. What you did in CS1 is you probably used some of these structures without really knowing what was going on underneath the hood. You just simply used the list, or you used the queue, or you used a tree, or whatever it was. You've probably used these data structures before, like lists, dictionaries, maps, sets, queues, stacks. But this course, we're going to open those structures up, and we're going to see how they actually work on the inside. What does a queue really look like when you actually implement it? What is a hash table? How does a dictionary work? Why are trees organized the way that they are? Once you understand these underlying ideas, you sort of stop treating these data structures like this magical black box that you just use. Rather, you start understanding why they work. And eventually, hopefully, you'll be able to design entirely new data structures whenever a problem requires a new data structure to be implemented. And that's a really big picture of what this course is. So we're going to learn a lot about how data is organized. We're going to learn about how algorithms are written to manipulate that data. And then we're going to look at evaluating solutions that are most efficient and sort of effective for the problem that we have at hand. So what are some of the differences between Java and Python? Many of you are coming from CS1, and CS1 you learned Python, so that's why we focus on Java versus Python. So what are these differences? At a very high level, both of these languages are considered what we call an object-oriented language. So it's an object-oriented programming language. Both of these languages support things like variables and loops and functions and if statements. So when you first look at both of these languages, they are going to seem very similar to each other. But there are some very important differences between the two. And one of the biggest differences right away is what we call typing. So in Python, a variable can hold almost anything. You can just say, I just want x to be 5, and not a problem. And then later on, you're like, you know what, I don't want x to be 5 anymore. I want it to be hello. You can do this in Python, and Python is perfectly happy with this. Java, on the other hand, well, works a little differently. Java says, nah, you can't do that. When you create a variable in Java, you have to tell Java exactly what type of data that variable is supposed to hold. If it's supposed to be an integer, well, then it's an int. If it's supposed to be a string, well, then it's a string. So Java is going to help you enforce these rules of having a variable be a specific kind of value. Another difference that we have here is Java allows us to place restrictions on our variables. So some variables can be declared so that they can only receive a value once. And then after that, they become these read-only variables. So we'll talk about that later in the semester when we start to discuss things like constants and immutable data. So in Python, you can assign a variable as many times as you want. In Java, you can restrict that, and you can create these constants or immutable things. There's also a major difference in visibility. So in Python, if one file imports another file, it can generally access everything that's inside of it. Java is much more restrictive. A class can choose exactly what information it's going to expose to the outside world and what information remains hidden. So in Python, first.py can call anything in second.py, but in Java, first.java may be only able to call some of the functions that are in second.java. So this idea is going to turn out to be incredibly useful when we're building sort of these larger software systems, because when software grows to hundreds of thousands of lines or even millions of lines of code, controlling access is going to become quite essential. Finally, Python is traditionally considered what we call an interpreted language, while Java is considered a compiled language. I shouldn't say considered, it is a compiled language. And that's where we're headed next. All right, so we're going to take a look at what does it mean to compile a program. So what does it mean? Here we are. What does it mean when we say that Java is a compiled language? The process is actually fairly straightforward. There are really three major steps to compiling in Java and compiling in any language that is a compiled language. Step one, write the code. So this is going to be no different from step one in Python. Step one in Java is write the code. And this is the code that you're going to type into IntelliJ. IntelliJ is going to be the editor that we're going to be using in this course. The code that you write is the Java code that we can read and understand. All right. So step two then is the compilation. We're going to compile it. So the Java compiler takes your source code and it translates your source code into this thing called bytecode. It doesn't translate it directly into the machine language. So for those of you that are coming from C++, whenever you compile your C++ code, it is converting it down into assembly, which will then run on that particular machine. But that's not what Java does. Java creates this thing called bytecode. So bytecode can run on many different operating systems and many different hardware platforms. As long as you have a piece of software that can run that bytecode, you are good to go. All right, so this is sort of where a Java slogan comes in. You write it once and you run it anywhere. So once step two is done, once the compilation is complete, we move on to step three. And step three is just simply run it, right? Run the program. So the computer executes the bytecode. It accepts any necessary input. It performs any of the calculations that it needs to perform, and then it produces the output. So the overall process looks like this. You take your source code, you compile it. Once you compiled it down into bytecode, then you run it. So the execution is going to be printed out to the screen or do, maybe print to a file or whatever it is. Now, for better or for worse, IntelliJ is going to hide much of this process from us. All we're going to do is we're going to hit a play button, and it's going to automatically compile our code for us. So once we hit that run button, everything is going to appear to happen automatically. But it's important to realize that these are the steps that are happening behind the scenes. Okay? So many of the error messages that you're going to see this semester are what we call compiler errors. And we'll get to that later on as the semester goes on. So understanding this distinction between compiler error and runtime error is going to save us a lot of frustration later on in the semester. Okay, so we'll take a look at some of these compiler errors, and we'll see if we can minimize how many of them we have throughout this term. Okay, let's take a look at the very basic structure of a Java program. One thing that you'll notice very quickly is that Java has more structure than Python does. Java likes things to be organized in a very specific way. Every executable Java program begins with a class. So we have this public class name. You're typically going to see something exactly like this. So public class name, where name is whatever you've chosen to call your class. Inside of that class, we're going to place functions. So we have functions that are inside of our class. The main function is going to be the starting point of our program. Whenever we start our program, we begin in the main function. You can think of it as, it's the front door to your program, right? It's the first thing that's going to happen. So you'll often see it written as public, static, void, main. And then you have string with 2 square brackets, and then args. And args is a variable. You can call it whatever you want, but most people will use the word args. If you don't, you're breaking convention, and it'll be very, very strange if you don't do that. So if this first line here, and when I say first line, I mean first line in the class. If this looks a little strange right now, that's fine. So right now, we're not too worried about what every little piece of a Java program looks like. We'll figure out those details later. For now, just recognize it as a standard form of what a main function has to look like. So inside of that main function then is where we have our statements. So we have our things like variables, variable assignments, maybe loops, maybe if statements, maybe there's some function calls in here, really any other type of command inside of our main function. So the overall structure looks like this. You have a class, and then inside of your class you have your functions, and in this case we just have one function, the main function. And inside of your function, you have statements. So that's the basic skeleton or template of nearly every Java program that we're going to write in this course. So we'll gradually add more pieces to this structure, as the semester sort of continues. All right. Let's talk about syntax. So syntax is simply, the set of rules that are going to define what a valid Java program looks like. It's the grammar of our language. And Java is very, very strict about grammar. So for those of you that are coming from Python, you're going to be frustrated with this because Python is very forgiving. Java is not. Java is very strict about its grammar. So unlike, you and I, if I make a mistake in, something that I say here, you're probably going to understand me. If I add an extra word or, as long as it's not a word that's too crazy, you can probably understand what I'm saying. But compilers, on the other hand, are not forgiving at all. If you make one small syntax mistake, the compiler is going to refuse to continue and say, nope, I expected there to be a semicolon. There wasn't a semicolon, so crash, all right? And it's not going to compile. So there are many, many syntax errors that can happen. And so what we're going to do here is we're going to look at some of the more common ones. So one of the most common rules in Java is that every basic Java statement is going to end with a semicolon. So for example, I could say something like, int x equals 5. Well, then there has to be a semicolon at the end. Or maybe a Boolean y equals false, then there's a semicolon. So notice that semicolon at the end. If you forget that semicolon, the compiler is going to complain. Another rule that's very important here involves curly braces. So the curly braces that you see here. So curly braces define what we call blocks of code. Classes use blocks, functions use blocks, loops use blocks, if statements use blocks. You're going to have blocks everywhere. The thing to remember is that every opening brace, so every opening brace is this left curly brace, should eventually have a matching closing brace or a right curly brace. If those braces don't match up, the compiler is it's not going to be happy. Right? It's going to have a very bad day if you don't have your left parenthesis or left curly brace and a matching right curly brace. All right, and if the compiler is having a bad day, clearly you're also going to have a bad day. All right, so make sure you have the same number of left curly braces as right curly braces, and then, well, at least you have that good to go. Another very common mistake here involves the naming of things. So variable names, class names, method names, they have to follow Java's naming rules, which we're going to see a little later on. Okay, so right now, just know that there are rules for what you can name your variables, and we'll talk about what those are a little bit later. One rule that might surprise many of you is that the file name and the public class name have to match. So what we saw in the previous example here was public class name needs to be in a file called name.java. So if you call your file, say, homework1.java, then the class inside of there needs to be public class homework1. All right, now we'll talk about what classes are later on in the semester, but for now, that's just a good rule to remember. If your file is called, test.java, then your public class is going to be named just public class test. Whenever you violate these rules, the compiler is going to generate what we call a syntax error. So you're going to have a syntax error whenever you violate one of these rules. So what this means is that essentially the compiler couldn't understand the structure of your program. The compiler just said, I don't know what you're trying to tell me. So one thing that you're going to discover this semester is that programming is often less about writing code, and it's actually more about debugging code, because everyone is going to have syntax errors. All right, everyone's going to forget a semicolon. You're going to have, too many extra parentheses. Maybe you have 4 left parentheses and 3 right parentheses. Right, you're going to mismatch your braces. All right, and that's fine. All right, the goal here is not to avoid these mistakes completely, because everyone makes them. So it's not a big deal. All right, don't worry about it if you make some small mistake here with the syntax. The goal of this course, and hopefully as you work your way through the major here, is to become good at finding them and then fixing whatever the mistake is. Okay, and that's just a skill that's going to improve as you practice and do this over and over and over again. One of the most useful statements in all of programming is just the print statement. And honestly, it's probably the statement that you're going to use the most, when you're learning how to debug programs. So in Java, the most common version looks like this. It's system.out.println. And we usually just say println for short, right? It's a println statement. What it does is it's a very simple statement. It just prints a line of output to the console, and that's it. So if you say system.out.println hello world, then the words hello world are going to appear on the screen. What you see on the screen here is system.out.println text. Well, that's just going to print text to the screen. So one common use of the println statement is when you're debugging your code. Suppose you write 100 lines of code and you want to know, is my code getting to line 70? So you want to know whether or not your code is reaching a particular location. What you can do is you can just simply insert a system.out.println or println statement that says, I made it, right? I got here, and then run your program. And if you see that message appear to your terminal, your console, then you know that that part of your code actually executed. But if you run your code and that message never appears, well, then you've learned something useful too, right? You've learned that that chunk of code that you expected to run didn't actually run. You can also just print out a blank line. So this is another common thing to do if you're trying to space your output and make it look, pretty. So if you're interested in your output being spaced correctly, making it easier to read, you use a system.out.println, and then you just don't put anything inside of the parentheses. So later in this course, we're going to use println for more than just text. We're going to print out things like integers and values, doubles, strings, booleans. Eventually, we're going to print out objects. So we're going to have a toString method that we're going to see later on in this semester. The takeaway from this slide might be this. If you're ever confused about what your program is doing, then one of the first things that you should try is printing information to the screen. Print out something like this, or print out a variable name. Okay, professionals do this all the time. Okay? It's one of the simplest debugging techniques that you're ever going to learn. Comments. So comments are notes that our programmers write for other humans. All right, it's not for the computer. It's not for the compiler. It's not for Java. It's just written for other people, right? The people on your team, the people that are reviewing your code. So a comment is simply a piece of text, that explains what your code is doing. Good comments make your code easier to read. They make it easier to maintain. Good comments also make your future self much happier, because I can promise you this: in 6 months, if you go back and look at one of your old programs, and I can almost guarantee you're going to think to yourself, who wrote this garbage? I have done that many times. Well, maybe not so recently, but I've done this many, many a time, where I go back and I look at some code and think, who wrote this? This is terrible. But then you're going to realize, oh yeah, I wrote this. Comments are going to prevent that. So comments are going to be the thing that are going to tell you, oh, that's what I meant to do with this function, or that's what I meant to do with this class, or whatever. Because if you come back to it the next day, sure, you're probably going to know what you wrote the day before. But if you come back to it 6 months later, a year later, it's going to be a lot more difficult to remember what you did 6 months ago. So the important thing to remember here is that comments are ignored by the compiler. Okay, they're never executed. They never become part of the bytecode. They really have no effect on how your program runs. So how do you write comments in Java? Well, a single line comment looks like this, right? It's these 2 slashes. So you have 2 slashes and then some line of text. Everything that comes after those slashes are just simply comments. They are ignored by the compiler. If you have longer comments that you wish to write, you do this slash followed by a star. And then you write a whole bunch of text, and it may span multiple lines. So as you see down here, you can have multiple lines. And then you end it with a star and a slash as well. So this lets us write comments that span multiple lines. One thing to be careful about when you're writing comments is don't just restate the obvious. So if you say something like, here's my statement, x equals x plus 1. And then you write a comment after that saying, add 1 to x. Okay, that comment probably isn't needed, right? That comment isn't going to tell us anything useful. So good comments are going to explain why something is being done, not merely what the code is already doing. So we'll talk about more about commenting style later on in the semester. In CS1, you worked with different types of data. The difference is that in Python, those types, were often hidden from you. Java makes those types much more explicit. So every variable in Java has a type. And the type tells Java exactly what kind of information is allowed to be stored there. And it also tells Java exactly how much space to allocate for that particular variable. So now Java isn't left wondering, do I need 4 bytes for this? Or 8 bytes? Or 32 bytes? How many bytes do I need for this particular data? When you tell Java what its type is, it knows exactly how much space to allocate. One of the most common ones that we're going to be using here is what we call an int. So an int stores whole numbers, things like 5, or -12, or 42, -3, 0. All of these things are integers. If you need decimal values, then you typically use something called a double, or a float that we're going to see later on in this video. So examples of doubles are like 3.1 and -0.25 or 9.4 e to the 3, so times 10 to the third power. This is another data type that is available to us in Java. These are very common ones, ints and doubles. If you need to store a single character, then you use something called a char. So a char is just simply the character A, or maybe X, or a question mark, or a new line. It can be any single character. So notice that in Java, single characters have the single quotes. So make sure that you don't put double quotes for a character because it won't work. You have to use single quotes for your characters. And then finally, if you want to store a logical value, you use something called a Boolean. So a Boolean can only store one of two values. It's true or it's false, and that's it. So these 4 types are going to show up constantly in all of your Java programs. There are other types that are available, but these 4 are kind of the top 4 ones that you should know about, and they're the best ones for just getting started here in Java. But as we continue throughout the semester, we're going to see that choosing the correct data type is often as important as writing the algorithm itself. If you only need values between 0 and 10, well then don't take an int, because an int is going to waste a lot of space, especially if you're storing thousands and thousands of these values. Do you really need an integer array? Maybe not. Maybe you can use a byte array or a short array or something better than that. So choosing the correct data type will help us use the correct amount of memory so that we're not wasting a ton of space. One thing that causes a surprising number of bugs is what we call mixing different data types in some expression. So you have these mixed types. So Java has rules for how these mixed type operations are supposed to work. So for example, let's say that I have 4.2 times 3. If you have 4.2 times 3, the expression contains a double and it contains an int. Since one of those values is a double, Java is going to convert that integer into a double automatically. So Java converts 3 into 3.0, and it's going to do the multiplication. So it's going to multiply 4.2 times 3.0, which gives us 12.6. The situation that causes the most confusion is what we call integer division. So think about this example. Let's say I give you 10 divided by 3. If I give you 10 divided by 3, you're probably going to expect this to be 3.3333 and to infinity. But that's not what Java does. Right? Java does not do this. And a lot of programming languages do not do this, where you do an int divided by an int. Because both of the operands, okay, so this is an operand, this is an operand, this is the operator. So because both of the operands are integers, Java performs what we call integer division. Because we're doing integer division, the decimal portion is discarded. So the result ends up just being 3. All of these 0.33333's just disappear, and you end up with 3. So you don't round it, you don't approximate it, you don't truncate it. The fractional part is just thrown away. And this catches students every semester. Okay? So if your calculations suddenly look weird and they look wrong, one of the first things that I recommend checking is whether or not integer division occurred somewhere in your expression. So the example that we see on the slide here demonstrates this idea, is that type conversions are happening one operation at a time. So Java doesn't look at the entire expression and then decide, oh, well, the entire expression is going to end up being a double, so I'm going to use a double in every single operation. Instead, each operation is evaluated according to the normal order of operations. So this means that expressions can change types as they are evaluated. Okay, so that's why we're going to take a look at this little example here. So this one, we do the multiplications and the divisions first, because that has the highest precedence. And the order in which you do them is from left to right. So the first thing that happens is you do 7 divided by 3. Well, what's 7 divided by 3? Well, 7 is an int, 3 is an int, so therefore we do integer division. And 7 divided by 3 is 2. Well, it's actually 2 point something, but we get rid of the point something because it's integer division, so we end up with 2. So our expression turns into this. Our expression turns into this thing. And then we ask, great, now what expression do we do next? Well, because of the order of operations, we're going to do this. We're going to do 2 times 1.2. 2 is an integer, 1.2 is a double, and so therefore we end up with 2.4, a double. So 2.4 plus 3 divided by 2 is our next expression that we have to deal with. Now we're going to do 3 divided by 2 next. Well, 3 divided by 2 is an int divided by an int. Well, an int divided by an int is just an int, so 3 divided by 2 is 1. We do 2.4 plus 1, and then we end up with 3.4. So just be careful about doing integer division. The result is an int. So what exactly happens here when Java mixes these different numeric types together? What Java is going to do is it's going to follow a set of promotion rules. And the easiest rule to remember is this one. So rule number 1, any operation that has a double produces a double. So if it's 5 plus 2.5, you're going to get 7.5 because the integer is being promoted to a double. So let me write that out, 5 plus 2.5. So if this is an int and this is a double, you end up with 7.5, which is a double. So that's rule number 1. Rule number 1 is the easiest one. If you have a double, you're going to end up with a double. Rule number 2. Well, what if you don't have a double? If you don't have a double, but you have a float, then it's going to produce a float. So with this example, we could see like 5 plus 2.5f, you're going to get 7.5f. And the f here is just signifying that this is a float instead of a double. So anything that isn't a double, but if you have a float in it, it's going to produce a float. And these things could be flipped as well. So this could be 2.5f plus 5, and that would be 7.5f as well. The third rule then is this, is that if you don't have a double nor a float, but you have a long, then the result becomes a long. So a long is just an integer type, but it's just a bigger integer. So an integer can hold roughly up to 2 to the 31, whereas a long can hold 2 to the 63, again, roughly. Okay, so a long is just a long integer. You can store more integer values inside of a long. Now you're using more space, but you can store more information inside of a long than you can inside of an int. So that's what a long is. So that's rule number 3. If you don't have a double and you don't have a float, but you have a long, well then it's going to produce a long. One kind of strange consequence of this rule is the last rule. And the last rule here is when you have smaller integer types. So if you don't have a double, and you don't have a float, and you don't have a long, then you're going to produce an int, no matter what it is. So even if it's something smaller than an int. So an int is something that can store up to 2 to the 31, again, roughly. Whereas a short is something that can store 2 to the 15, again, roughly 2 to the 15. You have these integer data types that are smaller than ints. So what happens if you add two of those things together? So I'm going to create two shorts. Short first equals 5. Short second equals 5. And then short third equals first plus second. No. All right, Java is going to give you an error. And the reason you're going to get an error is because it's going to promote both of these variables to be an int before it does the arithmetic. So before the operation, this thing turns into an int. This thing turns into an int. And so when you do first plus second, what you have is an int plus an int. What that's doing is it's producing an int. So this is the one that feels a little weird, the first time you encounter it. But it's just one of those rules that kind of becomes second nature once you see it again and again. So don't fret too much about these weird rules showing up in Java. This is just one of them, and there won't be many of them. So this is one that you just need to remember, is that if it's not a double, not a float, not a long, you're going to get an int. So the big takeaway from this slide is that Java is constantly performing these type conversions behind the scenes. Most of the time, these conversions are going to help us. Occasionally they surprise us when you have something like this happening. But when something unexpected happens in some calculation, understanding these promotion rules will often explain why that particular strange thing happened. Right. So let's talk about variables. Variables in Java are a little bit different from what you've seen in Python. In Python, you can pretty much, just start using a variable whenever you want. You want to say x equals 5? No problem. Python's going to figure out what the type is automatically. Java doesn't work that way. Before you can use a variable, you have to tell. So you must tell Java what kind of data that variable is going to store. So this is what we call a declaration. So you're declaring your variable type you're declaring your variable to be some type. So the general form looks like this. You just simply say type and then the name of the variable. And you don't need to have equals value. So you could say something like int x. So I'm declaring x to be an int, or short y. I'm declaring y to be a short, or double z here. I'm declaring z to be a double. So this is a declaration. We are declaring this variable to be a particular type. So once we've done this, at this point, we've told Java that, this variable exists, but we haven't actually given it a value yet. So assigning a value to a variable is what we call initialization. Okay, that's step 2 here. Very often you're going to combine these steps into one single statement. So you'll often put your declaration and your initialization into a single statement. So you could say int x, and then later on in your code, x equals 20, or you can just say int x equals 20. So that's what we see on the examples on the slide here. Double my GPA equals 3.19, or int x equals 11 mod 3 plus 12. So let's take a look at the second example, because this mod operator just showed up, which you may or may not have seen before. You may have seen this mod, or when I'm saying mod, it's short for modulus. I think that's spelled right. The modulus operator. So the modulus operator is represented by the percent symbol, and it returns the remainder after the division. So for example, when we do 11 divided by 3, 11 divided by 3 equals 3 with a remainder of 2. So 11 mod 3 is just simply 2. So this means that 11 mod 3 plus 12 is equal to 14. And the reason that it's 14 is because 2 plus 12. So therefore x ends up being 14. This modulus operator is going to show up surprisingly often in computer science. We're going to use it later for things like determining whether or not a number is even or odd, when we cycle through arrays. So if we get to the end of the array and we want to go back to the start, How do we go back to the start? Well, we use the mod operator. Hash tables, we're going to use mod all the time, and almost every method we write for a hash table, we're going to use a mod. And many other algorithms. So we're going to see modulus a lot throughout the semester. So if it's unfamiliar now, don't worry about it. We're going to see a lot of practice, so just kind of put that in the back of your mind that modulus will come up quite a bit in this course. One important rule that Java has here is that variables can only store values that are compatible with their declared type. So for example, we have this int x equals 2.5. That's not legal. And the reason that it's not legal is pretty simple. An int can't store decimal values. All right, if Java were to have allowed this, then what should happen to the 0.5? Do you round it? Do you truncate it? Do you round it up? So these different choices are going to produce different answers. And so instead of having these different choices that could be made, Java just simply says, nah, I ain't going to do it. All right, so Java is going to refuse to guess. Instead, it's just going to generate an error and say, I don't know what to do. But the reverse is perfectly legal. So if you want to store 4 into a double, not a problem. So storing an int into a double works just fine. And the reason that it works just fine is because you're not losing any information. Again, think about the first example. How would you store 2.5 into an int? Well, what do you do with the 0.5? You have a lot of questions that you don't know what to do with. But here, there is no question. Can you store 4 into a double? The answer is yes. And the answer is just 4.0. One thing that's confusing, which is why I have it up on the slide here, is what do you get when you do double average equals 11 divided by 2? So a lot of students expect the answer to be 5.5. But it's not. Right? That's not what happens. So remember, Java is going to evaluate the right-hand side first. So Java is going to take this 11 divided by 2 and compute an answer. Since both of these operands, so the 11 and the 2, since both of them are integers, Java performs integer division. When you do integer division with 11 divided by 2, you get 5. You don't get 5.5. So only after that value's been computed does Java then take it and then convert it into a double. So what Java is actually doing is it's saying, take this statement and then turn it into this. So double average is equal to 5. And then it's taking this 5 and turning it into 5.0. So this is one of the common mistakes that I see often, which is why I include it in this slide. And honestly, it continues showing up in programs, through the end of the course. I see this again and again and again, which is why I'm hoping that highlighting it now will make you think twice about it. The thing to think about is whenever your arithmetic looks strange, check for integer division. All right, this is often going to be a source of bugs later on in this course. There are a few additional rules about variables that Java is going to enforce here. First is that a variable cannot be used until it's been assigned a value. So consider this. You have int x, and then you print out x right away. What is the value of x? I don't know. It's going to generate an error. Right? Java has no idea. Okay? Java has no idea what x is because we never gave it a value. We declared it, but we never initialized it. So Java is basically saying this. You told me that a variable exists, but you never told me what value should go inside of that variable. And so because of that, Java just says, I don't know what to do, and I quit. Right? So you get an error. Another important rule is that you cannot declare the same variable twice within the same scope. So we're going to talk about scope in a few minutes here. So don't worry if you or you're not sure what scope is. We'll get to it eventually. But if you try and create two variables that have the same variable name, like int x, and then right after it int x, Java is going to say no. Right? This is illegal, right? Because x already exists. So trying to create another one doesn't make a whole lot of sense because you already have one. You already have an int x. Don't create it again, or don't declare it again. Similarly, you can't create or declare two variables that have different types but have the same name. So here we have int x equals 3 and then int x equals 5. If you want to do this, then what you want to do is get rid of this int. Right? You just want to change x to have a new value of 5. don't redeclare it. Don't give it another name. Something that I see people do often is they'll say something like int x equals 5, and then maybe double x equals 7.3. If you try and do this, that's also illegal. Right? You can't create the same variable in the same scope. Now I keep using the word scope. Now we're going to discuss scope in much greater detail in a few minutes here. So for now, just think of scope as it's the region of the program where some variable exists. Okay, so the takeaway from this slide is quite simple, I hope. You declare variables before you use them. You initialize variables before you actually read them or use them. And you don't declare a variable twice in the same scope. So you follow these rules, and you're going to avoid a lot of headache later on. All right. Earlier we talked about those 4 common primitive types, those data types of int, double, char, and boolean. But Java actually provides several other primitive types as well. One of these is what we call the long type. And we talked about this a couple of slides ago, but I'll just emphasize it more here. A long is just simply a larger integer. So an int uses 32 bits of storage, whereas a long uses 64 bits. So what this means is that a long can store much, much larger numbers. Now, if you're curious about what this means about bits and bytes and all that, computer organization. Right? Take that course, you'll learn all about what it means to represent numbers inside of ints versus longs. So let's say we're using a long, and we want to write or create this very, very large integer type. When we're writing a long literal, so this thing is called a literal on the right-hand side, you add the L to the end of it. Okay, so this is specifying that this thing is a long. So we're telling Java, I want this value to be treated as a long. Don't treat it as an int, treat it as a long. Another type that we have available in Java is what we call a float. And a float is just a smaller version of a double. It's doing the same thing that a double does, but it uses less memory and it provides less precision. So similar to ints and longs, a double has 64 bits, whereas a float has 32 bits. Now a float literal is going to end in an F, so this tells the compiler that 123.45 is a float and not a double. A couple of other data types here are a byte and a short. A byte can store anything between -128 and 127. And the reason is because it only stores 8 bits of storage. If you try and store a value outside of this range, Java is going to complain, and rightfully so. We also have a short. So a short here uses 16 bits, and we can store larger values rather than a byte, but still smaller values than an int, because an int is 32 bits. Now, a natural question you might be thinking about is this, why would I ever use a byte or a short? Why can't I just use an int all the time? Or why don't I just use a long all the time? And the answer to that is, most of the time, it probably doesn't matter. Modern computers, your phone, your tablets, your desktops, laptops, these things have tons of memory. So using an int is usually just the simplest choice. But, let's say you work for some company that has, some embedded system. So now you're working on these really, really small devices that have, 32 kilobytes of memory or storage available. So if you're working with a lot of data, or you're writing this low-level software or dealing with these embedded systems where you have very limited memory, now your memory usage becomes important, and you can't just simply say, I'm just going to use an int all the time. I'm just going to use a double all the time. So that's when these smaller data types are going to become very useful. Okay, are they going to be terribly important in this course? Not necessarily. We're not going to get to the point where we're going to have to use a short instead of an int, otherwise our programs will fail. But these are things to keep in the back of your mind, is that if you know your data is between this, well, then use a short. If you know your data is between this, well, then use a byte. So we'll use these types occasionally in this course, but for the majority of the time, we're going to use those 4 that we saw on the slide previously. We're going to use int, we're going to use double, we're going to use boolean, and we're going to use char. The next piece of syntax that we need to learn about here is the if statement. And the good news is that you've already seen this before. Whether you're coming from Python or C++, the logic is exactly the same. The only thing that's really changing here is the syntax. The underlying concept is identical to what you already know. An if statement allows us to make decisions. It allows our program to execute some code only when a particular condition is true. So the general structure of an if statement is going to look like this. It's going to be if, and then inside parentheses we're going to have some test or some condition. And then if that test or that condition is true, we have some statements that we're going to execute. Now notice two important things here. First, the condition goes inside of parentheses. Okay, so you need a left parenthesis and a matching right parenthesis. And the second thing then is that your if block, or the code that's inside of your if statement, needs to have a left curly brace and a right curly brace. This is not Python. In Python, you indent. In Java, you need these curly braces. The condition itself, so the test here must evaluate to true or false. Okay, it must be a true or false statement in here, which if you're coming from C++ is going to be a little bit different. In C++, you had integer values that you could put in here. Coming from C, you could have an integer value in here. You can't do that in Java. In Java, you have to have a Boolean expression for your test, your condition. So for example, on the bottom here, let's say you're reading in the GPA from the console or from the terminal, and you want to know whether or not the person has had their application accepted. So if GPA is greater than or equal to 2.0, then we print off this text where we say application accepted. Whereas if the GPA is less than 2.0, well then we don't do it, right? We don't print out this statement. So one thing that I notice that people forget is that the statements inside of an if statement are only executed when the condition is true. So if the condition is false, Java's just going to skip it. Right? It's going to jump to whatever is the code immediately after the right curly brace. So this idea is hopefully very simple. You've seen this before, but every program that you write for the rest of your life is going to have some sort of decision making of if statements inside of it. So understanding how an if statement works is kind of one of the basic building blocks that you need when you're writing code. Sometimes we don't just want to do something when a condition is true. Sometimes we want one action where the condition is true, and we want a different action when the condition is false. So that's where the if-else statement comes in. And this should be similar to what you already know. Okay, there's nothing magical here that you haven't already learned in say, Python or C++. So the structure looks like this. The important things being the test condition needs to be inside of these parentheses. So if this condition is true, then you run these statements, else you run these statements. So if the condition were false, then you're going to run the statements in the else block. So exactly one of these two blocks is going to execute. You're never going to get both, and you're never going to get neither of them. Okay, it's always going to be exactly one of them. So if the condition is true, this is what happens. If the condition is false, this is what happens. So consider this example that we have on the bottom here. On this bottom example, we read in the GPA from the terminal again, like we did on the previous slide. And then we test if the GPA is greater than or equal to 2.0, then we say passed. And if it wasn't greater than or equal to 2.0, then we say, well, that's unfortunate, right? Not passed. So notice that there's no situation where both of them are going to appear, and there's also no situation where neither of them appear. Exactly one of these branches is going to happen. So when you're writing programs, it's often useful to think of an if-else statement as like a fork in the road, right? The program is going to reach some condition, and it's either going to go left or it's going to go right. It's either going to be true or it's going to be false. So as we continue throughout the semester and in this course, we're going to be building much more complicated things. It's not just simply going to be do one if-else statement, but it will be much more complicated than this. But they're all building on this very, very basic idea. The next structure that we're going to take a look at here is what we call a switch statement. And this is one that you may or may not have seen before, right? I find that many people who start this course haven't seen a switch statement before, and that's fine. We'll see it today. So a switch statement is often used when you have a variable that can take on a fixed set of values. So for example, let's say you have days of the week, or some menu choices from some you're ordering from some restaurant or something, or maybe some selections that you're making where it goes from maybe 1 to 10, or like status codes of some operating system program, things like that. So if you have a fixed set of values that you're choosing from, that's a good time to use a switch statement. So what does a switch statement do, and how does it look like with something that you already know? So on the right-hand side, you have an if statement. So you have your traditional if, else if, chain of statements on the right. But on the left side, we have an equivalent switch statement. Both of these pieces of code are going to do exactly the same thing. So if the value of day, so we're going to read in day, and day is going to be 1, 2, 3, or something else. Right? And if it's not 1, 2, or 3, well then I guess I don't care what it is. So if the value of day is 1, well then print out Monday. If the value of day is 2, then print out Tuesday. And I shouldn't say if, I should say else if. Else if the value of day is 3, print out Wednesday. Else, if it's not 1, 2, or 3, print out invalid day. That sequence of code is exactly what's happening in your switch statement. So in your switch statement, the syntax looks like this. Okay, it's just a cleaner way of expressing the exact same logic. So the syntax starts with this. It starts with switch day, which tells Java which value are we examining. Then we define a sequence of cases. So we have, I should say, maybe a series of cases here. So we have case 1, case 2, case 3, and then we have this default thing at the bottom. Each case is corresponding to a possible value that day could be. The thing that usually catches students when they first see this is this thing called a break statement. Okay, so a break statement is this. After a case finishes executing, the break immediately exits the switch statement. So what a break is doing is it's saying, all right, well, let's think about what this is. Let's say day equals 1. We're going to switch on day, and then we're going to say, does day equal 1? Ooh, it does. Great. What do we do? Print out Monday. What do we do next? We break. When we break, what do? We take our execution all the way down here. So we take it to the end of our switch statement, and then we start executing whatever's down here. So that's what these break statements do, is they jump down to the first statement that is after the switch statement. If you don't have a break, well then Java's just going to continue executing to the next case. And that's actually what we're going to see on the next slide, so I'll sort of leave that for a minute from now. Lastly, notice the default case. So the default case here is essentially the else case in the if, else, if, else, if, else chain. So the else that we have here is our default case in our switch statement. So default case is essentially the same thing as else. It handles anything that didn't match one of the earlier cases. One of the features of a switch statement that you don't have with an if statement is the ability to fall through. So this fall through behavior is why you might want to use a switch statement instead of a bunch of if statements or if else logic. So to understand a fall through, we need to think about a case label in a switch statement as more of just jumping to a location, completing a block of code and then jumping out of it. Okay, that's not what a switch statement does. What you can think of it as, what a case is it's just a label inside of the switch statement of where you jump to and then you start executing. So when Java finds a matching case, so here when we have level, we're going to search and say, does level equal this? Does level equal this? Does level equals this? But then once it equals that, we're just going to start executing. And we're not going to leave until we find a break. Now that's very different from what your if statements are doing. Your if statements are saying this: if level is less than or equal to 3, and level is greater than or equal to 1, then we jump inside of our if statement. Then we check if level is less than or equal to 1, we print out bronze. If level is less than or equal to 2, we print out silver. Then we print out gold. So on the right-hand side, if level equals 1, then this is true, right? Level is greater than or equal to 1. If level is less than or equal to 1, what do? We print out bronze. since we don't have an else if, we have an if here. So we're just going to check this as well. Is 1 less than or equal to 2? The answer is yes. So print out silver. And then last we print out gold. So if level equals 1, on the right-hand side, we print out bronze, we print out silver, and we print out gold. Well, how does it look in the switch statement? So notice what happens on the left-hand side in our switch statement. Since there are no break statements after case 1 or case 2, that means execution is just going to keep falling to the next case. So let's say level does equal 1. What Java is going to do is it's going to say, all right, well, level equals 1, so jump to here. And I probably shouldn't have a 2 here. This should probably be, read in from the console. Don't just assume level equals 2. Okay, so let's assume that level equals 1. When level equals 1, what do? Well, we come here, and then we execute this statement. So we print out bronze. But since there's no break statement, we're going to execute silver as well. Since there's no break statement, we're going to execute gold. So when level equals 1, we get bronze, we get silver, and we get gold. Exactly what's happening on the right-hand side. So because we had no break, level 1 prints out bronze, silver, gold. If level equals 2, then on the right-hand side, you're going to get silver and gold. On the left-hand side, level isn't going to equal 1, but it does equal 2, so we print out silver and gold. It exits because we have a break, and then we're done. If level equals 3, then we're only going to print gold, and if level equals 3, we're only going to print gold. So this behavior often surprises students from what I notice, the first time that you see it. One of the most common bugs that you have with switch statements is forgetting to put a break statement. But this fall-through behavior can be extremely useful, because sometimes you do want multiple cases to share, some behavior. And when that's the goal, the fall-through actually lets you write very concise code that you can't do on the right-hand side. So you'll notice the right-hand side, you have a whole bunch of if statements, you got some nested if statements, whereas on the left, it's just this really nice 3 cases, and that's it. So the big takeaway from this is this, from a switch statement, is a switch statement stops whenever you hit a break statement. So whenever you hit a break statement, you jump to the end. All right, that's one of the major things to remember from this slide. If there is no break, then just keep on going. All right, execution just keeps going until you get to that, until you see a case, or until you see a break. All right, and then it will stop. Before we can really use things like, if statements, for loops, while loops, we need some way of asking questions like, is this thing equal to this or less than? We need a way to get our Boolean conditions. So we need a way to test whether something is true or false. And this is where relational expressions come into play. So the operators that you see on this slide, you're probably familiar with, from Python and C++. In Java, you have equals operate the equals operator, meaning equals. Do 2 things equal each other. You have the exclamation point equals, meaning not equal. You have less than being less than, greater than being greater than, and so on and so on. Things you probably already know from your previous language. So these operators will always evaluate to a Boolean value. It's always going to be true or false. So 5 less than 10, of course, is true. Whereas if you say 7 equals 3, then that's going to evaluate to false. So one thing that students will sometimes accidentally do is that they will assign, or they'll use a single equal sign when they mean to use a double equal sign. So remember, a single equal sign means assignment, whereas a double equal sign means comparison. They are completely different operations. And that's a mistake that everybody's going to make at some point. So don't worry. If you make that mistake, trust me, everyone else has made that exact same mistake of using one equal sign when they meant to use 2 equal signs. Now Java's a little more forgiving because you're only allowed to have Boolean variables inside of here, but other languages are less forgiving. So if you're coming from C, you'll know this, that if you only have 1 equal sign in here, well, it turns out it's going to run, and it may not be what you expect it to be. So these relational operators, they're really just the building blocks that let our programs make decisions. Without these building blocks, every program is just going to do the same thing, all right, all the time. So we need these relational expressions to be able to make decisions of doing one path or another. This slide is one of those things that may seem really strange the first time you see it, and honestly, it catches a lot of experienced programmers as well. All right, this isn't just a beginning programmer issue. There's a lot of experienced people that will fall for this often. So know about it now, right? Learn it and sort of internalize it and remember that this is an issue. So suppose we write this. I'm going to say double A equals 0.1, right? 0.1 plus 0.2. Then I'm going to say double B equals 0.3. Then I ask this question, does A equal B? Well, because I'm talking about it in these terms, you're probably not going to think that it's true, but what does this print out? You would think that this is true, okay? If I wouldn't have said anything, and if I wouldn't have set this up, and I would have just asked you, does A equal B? I imagine most of you would say yes. You would look at this and say, let's see, 0.1 plus 0.2 is 0.3, B is 0.3, does A equal B? Yeah, of course they equal each other. That's not what happens. So Java is going to say, ooh, that's not going to do that. It's going to say no, it's false. A and B do not equal each other. Now the reason behind this is that the way that you represent floating point numbers in the binary system, it can't do it exactly. So there are a lot of decimal values that cannot be represented exactly in this binary system. Rather, they're stored as these very, very close approximations. So what actually gets stored for 0.1 and 0.2 isn't going to be exactly 0.1 and 0.2, all right, in general. All right, I think one of these can actually be done, but I think the other one cannot. But it's something that's very, very close. So when these approximations get added together, the final result may not be the same bit pattern as the approximation for 0.3. They may be off by just a little bit. So the numbers are going to be incredibly close to each other, but they're not going to be equal to each other. And computers take this equality very, very seriously. Either every bit is going to match, or it doesn't. So if even one bit doesn't match, well then the computer says, nope, these two things are not equal to each other. And that's what's happening here. So 0.1 plus 0.2, I believe gives you something like this. And I could be mistaken, but I think it's 0.299999999, something like that. Whereas 0.3 does get stored like 0.3. So when you're asking if these two things are equal to each other, the answer is no. These two things do not equal each other. So how do you deal with this? Well, you deal with this by knowing that it exists. Okay, you need to know that this exists. And if and when you take computer organization, you will learn all about why this actually happens, right? And what's going on behind the scenes. For now, we're just going to treat it as a black box and say, I don't really know how this works. I just know that it's a problem and I need to deal with it. So in practice, when you have doubles or floats and you're trying to check if they equal each other, you usually don't test to see if they equal each other. You're not checking for equality. Don't check equals equals. Instead, you're going to ask the question like this. Are these values close enough that they're considered equal to each other? So maybe you say something like this. Maybe you'll say something like math.absolute value of A minus B. If this thing is less than 0.00000, put as many zeros as you want here, 1. And if this is true, then they are equal to each other. So this is a very common technique that you'll see throughout programming, the software engineering, sort of scientific computing here. Whenever you're dealing with floating point values, be very careful with the equals operator. It often doesn't give you what you expect. Usually you need some sort of hack like this, where you're just checking if they are very, very close to each other. Loops are another concept that you've likely seen before. The good news is that the logic hasn't changed. The only thing that's different here is the syntax. So a for loop has 3 parts. It has an initialization, it has a test condition, some Boolean, and it has an updating code, updating statement, I should say. And all 3 of these pieces are going to appear inside of the parentheses. So if we write, for int I equals, say, 10, and I is greater than or equal to 0, and then I minus minus, we have all of our steps here. We have our initialization of I equals 10, we have our test of I greater than or equal to 0, and then we have our updating code of I minus minus. So the initialization code runs once, this statement runs one time, then the condition is tested, so this is step 1. Step 2 then is check the condition. If the condition is true, step 3, execute the body of your loop. After the body executes, then you run the update statement, this I minus minus. Once the update statement runs, then you go back and you check the condition again, and you repeat this until the condition becomes false. So one way to think about a for loop is that it's just a really compact way of expressing this very common pattern that we're going to see. Initialize something, keep repeating while a condition is true, and then update after each repetition. And that's it. That's all a for loop is doing. So let's zoom in on what a for loop looks like. And we'll look at each of these parts, and then we'll continue on. In this example, we have I equals 1. So this creates basically a counter inside of our loop, and it gives us a starting value. And the loop counter is usually called I, or index, or maybe it's J or K. Right? This is often what our loop counter is going to look like. But that's just a convention. You don't have to call it I. If you want to call it counter, you can, or call it index. Right? Anything else that's a valid variable name is fine to use. Okay, the computer doesn't care what you call it. The name I is just popular. All right, it's a good convention, mostly because programmers are lazy. All right, I don't want to have to type out index, so why don't I just type I? Good enough. All right, call it I. The starting value is completely up to you. All right, many loops will start off counting at 0. Some are going to start at 1. Maybe some start at 100, so you can make your I be whatever you want it to be. It depends, entirely on the problem that you're trying to solve. So one thing to notice here is that the initialization just happens one time. So this is a one-time statement that happens. It doesn't happen every iteration. It happens once when the loop first begins, and that's it. And that's an important detail to remember. The second part then is our test condition. It's our Boolean statement. So in this example, we have I less than or equal to 6, and it's just a Boolean expression. That's all it is. It evaluates to true or false. If it's true, the loop is going to continue executing. If it's false, the loop stops. So imagine that I equals 4. If I equals 4, then we're checking is 4 less than or equal to 6? Well, that's true. So since it's true, the loop continues. Now eventually I is going to turn into 7, and at this point we're going to ask the question, is 7 less than or equal to 6? And the answer is false, and that's when the loop is going to terminate. So the test condition is essentially just the loop's exit strategy. All right? It's the thing that's going to eventually allow our program to move on past our for loop. The final part of our for loop then is the updating portion, or the incrementing step or decrementing step. This is the part that changes the loop variable, or it often changes the loop variable, after each iteration. So in our example here, we have I++. All right, and that's just shorthand if you've never seen this before for I equals I plus 1. All right, these two things are synonymous with each other. So every time a loop executes, I gets 1 larger. And eventually, that's going to cause our test condition to become false, because I starts off at 1, then it goes to 2, then it goes to 3, so on and so on and so on until it gets to 7. So this update step is extremely important, because if the update never changes, the value in any meaningful way, then the condition may never be false. So you need to be careful here that you don't end up with an infinite loop. So an infinite loop, if you've not seen it before, is exactly what it sounds like. It's just a program that keeps running forever, or at least until you force it to stop. All right, and everyone's going to write an infinite loop. Don't worry if you end up writing an infinite loop. Not a big deal. Everyone writes it. I have written many in my life. I still write many infinite loops, usually not on purpose, and then I realize, whoops, oh, that's an infinite loop. Okay. So let's see how this works. All right, let's see how this all works then on one more slide here, if I can get there. There we go. So let's walk through this example sort of step by step, just to see how a for loop works. Understanding the exact order here is really important, because you need to know which things are happening once, which things are getting repeated, and which things are happening again and again. So the first thing that happens here is I equals 1. That's the initialization step, and it's going to happen one time. So then we check, is I less than or equal to 4? So we go to step 2. So we do 1, and then we go to step 2. Step 2 is our condition. We check if 1 is less than or equal to 4. The answer to that is yes, so it's true. So we execute the body, and the body is just this simple print statement that prints out I and I squared and so on. So once this prints out, so we do the third statement here, then we go to statement 4. So we execute I plus plus. So then I becomes 2. Now we check the condition again. So now we go to statement 2, and we check is 2 less than or equal to 4? Yes. So we execute the body again. So we execute 3, then we execute 4, and then we test again, and we keep doing this and we keep doing this until I becomes 5. So this pattern repeats itself until we get to statement 2 and I becomes 5. So at this point, 5 is no longer less than or equal to 4. So 5 less than or equal to 4 is false. The loop is going to end. That's when we move on to statement 5. So eventually we move on to statement 5 and we say done. So understanding this execution order will make debugging your loops a lot easier later on in this course. Oh, now we're going through all the examples. Kind of forgot this was happening. All right, so there's the output, there's the output, there's the output, and there we go. Good. The last thing that we're going to talk about in this set of notes now is going to be something that we call scope. So scope is one of those concepts that at first might feel a little abstract, but once you understand it, a lot of your compiler errors are suddenly going to start to make some sense. So in this example, we have this variable called size. So I've changed my slide. There we go. I've declared my size variable inside of my main function. So the question is this: can these two functions access the size variable? So can top half and bottom half use that size variable? The answer to that question is no. All right, they cannot. All right, even though that variable exists somewhere in our program, so our size variable does exist, it exists right here inside of main, it doesn't exist inside of these functions. So it doesn't exist inside of the top half or the bottom half. So those functions are outside of the variable's scope. I can only use size from here to here, inside of this function. So this is a common misconception that people have with Java the first time that they're using it, is that once a variable is declared, then every part of the program can, automatically see it. But that's not how Java works. Okay? Variables only exist within a certain region of that code, and those regions are what we call scope. So what exactly is scope? All right, let's define what scope is. So scope is a region of a program where a variable can be accessed. A useful rule of thumb with scope is this, is that you find the variable declaration. So here I have my variable declaration. Then I'm going to work backwards in the code. So imagine there's a whole bunch of code above int x equals 3. Work your way backwards until you find that left curly brace that contains that variable. Find its matching curly brace. Find its matching right curly brace. So the matching right curly brace is, circle the wrong one. The matching right curly brace is here. The variable exists between here and here. So our x variable exists in this for loop, and it would exist down here if there were any statements that I had after the for loop. That's it. That's what scope is. So again, in this example, x is declared at the beginning of the function, so it exists throughout the entire function. But the variable I is declared inside of the for loop. So if I go here, x's scope is available inside of this entire example function, whereas I is only declared and available inside of the for loop. So I only exists inside of that loop. Once we leave the for loop, I no longer exists. So if we try to use I outside of the for loop, Java is going to give you an error. So think about your variables, at a high level, think about your variables kind of living inside these little boxes. And that's often helpful when dealing with scope. Whenever you leave your box, that variable's gone, and you can no longer use that variable again. So this slide shows us some important consequences of scope. In that first example, we have multiple variables that are named I, and at first glance, you might look at this and say, well, that's not right. All right, this seems illegal. I can't do that. But it's actually perfectly fine. And the reason for that is these variables live in different scopes. They're in these different boxes that they're available. So this int I is available from here to here. This int I is available from here to here. This int I is available from, well, right here where I declared it, to wherever the matching right curly brace is for whenever the left curly brace started up above it. Okay, so that first I only exists in that first loop. The second I only exists in the second loop, and the third I exists outside of the loop. So it's beneath both of those for loops. Since those scopes don't overlap, Java has no trouble figuring out which variable you're talking about. So if you're talking about I here, Java knows what you're talking about. If you're talking about I here, Java knows what you're talking about. If you're talking about I here, Java knows what you're talking about. Now that differs in the second example. So in the second example, we are trying to use an I outside of where it was declared, and we're trying to declare an I again where we already have an I declared, and we can't do that. So here we're trying to declare another I inside of a scope where I already exists. I already declared I here in the for loop. I can't do it again. So you can't say int I equals 2. All right, it's not allowed. And the reason it's not allowed is because Java doesn't know which one you mean. Right? If you were to say I later on, which I are you talking about? Are you talking about this one or are you talking about this one? Java doesn't know. So since Java doesn't know, it's not going to guess. And it's just going to say error. You have an overlapping scope. The last thing that we have here is noticing this I equals 4 at the bottom of our, or after our for loop. So because this is outside of our loop, it's going to produce an error. And the reason it produces an error is because the loop variable no longer exists. That I variable is gone. Its scope has ended, and sadly, the I variable has been killed off. And so if you try and use I outside of the for loop, it's not going to work. So scope is one of the main ways that programming languages can organize and sort of protect their variables. And as we move into larger and larger programs later in the semester, understanding how scope works is going to become much more important.